Okay, this is an informal approach to finding the derivatives of exponential equations. So in other words, we're finding derivatives of equations that look like y equals some base raised to an x, an exponential equation. We're not going to prove this. We're actually going to, we're rather going to show a relationship and use that relationship as an informal proof. But we'll prove this in subsequent lectures. All right, so what I'm going to ask you to do is um, try this exercise at home, and you could just watch, but I think it's worth your time to actually go through doing this. So what I want you to do is take out your calculator, and I'll draw, not draw, but get my calculator open here. Um, and then what it says is that into y1, we're going to put e of x, and then in y2, put the derivative of e to the x. So that's something that you guys know how to do. So do that in your calculator, and I will do that as well. And so we have y, and we have e to the x. And I'm just going to pause this to do n deriv to save some time. So here we have in y1 we have e to the x, and y2 we have the derivative of e to the x. And so what we're going to do is, through investigation, see the relationship between e to the x and its derivative. So I'm going to go press second table. Uh, and whoa, this is a pretty profound relationship that I'm looking at between y1, which is e to the x, and y2, which is the derivative of e to the x. So let's take a picture of that, because that's some pretty important stuff. You should be saying, "Oh my gosh," because what you see here is a key relationship, which is that the derivative of e to the x is, well, what is it? It's e to the x. Where am I going to put that? Right up here. So what this just confirms, what this confirms, here we have, e to the x, and here we have the derivative of e to the x. And we notice for all values of x, the derivative is the same thing as the function itself. So in other words, we just confirmed that the derivative of e to the x equals e to the x. And this question here, can you think of any other function for which this is true? Well, I mean, you could make some guesses and some conjectures, but let me just say that there are no other functions for which this is true. In other words, e to the x is the only function for which it has, for such that the derivative of e to the x is e to the x. Or in other words, it's the only function such that the derivative of that function equals the function itself. That's cool. Um, so what we could do, just to kind of start thinking about this table that I'm going to be filling in talking about the stretch factor, what I'm looking at are the y2 over y1 values. So in every case, if I took y2 and divided it by y1, 2.7 divided by 2.7, I'm going to get 1. For every single one of these values, if I divided y2 over y1, I'm going to get 1. And what we're going to start trying to recognize, or what we're trying to show, is that if I have, some function b to the x, that the derivative of b to the x is related, that the derivative of b to the x is related via just some stretch factor. Okay, so what are we going to do now? What we're going to do now is we're going to put each of these functions. Well, we already did this one. We're going to put each of these functions into y1 and look at the relationship between the function and its derivative. And just so I have more room, let's have another page. So what we're doing, we're going to go back into our calculator, and I want you to do this with me. And for y equals, instead of e to the x, let's put in 2 raised to the x power. Oh, shoot. And now let's go to the table. And let's snap a picture of this. Okay, so this is the values of 2 to the x and its derivative. And what we can start seeing is that there's going to be a relationship between y2 over y1. So this is 2 to the x, and this is the derivative of 2 to the x. And if I look at y2 over y1, so for the first case, like 0.69315 over 1, that's going to equal 0.69315. Now let's look at the second case. Um, I've got 1.3863 over 2. What does that equal? This also equals 0.69315. Interesting. So there's some relationship between the derivative, the stretch, or the ratio between the derivative and the function itself. And if we just did one more to look at it, we could do 2.7726 over 4, and oh my gosh, once again we get the same thing back. So the stretch factor of 2 to the x is 0.69315. Now let's do the same thing for um, ln, or sorry, for 3 to the x. So get out your calculator, and we're going to put in 3 to the x and look at the table. And I'll take a picture of this just so that we can see it easy. So now we're looking at 3 to the x and the derivative of 3 to the x. And once again, if we look at the ratio between the derivative and its function, in the first case we have 1.0986 divided by 1. Well, that's 1.0986. If we look at, when x equals 1, we have 3.2958 over 3. Well, that also equals 1.0986. And for each one of these y2 over y1 values, we're always going to get 1.0986. So what I want you to do is go. I want you to pause the video in a second, and what I want you to do is find the stretch factor for the function and its derivative for 4 to the x, and then for 5 to the x. So I want you to find these values. And what I'm going to do is pause the video and go ahead and find those already, so that when you unpause it, the answers will be there. But I want you to go through the work of actually finding this ratio. Okay, so I went ahead and let's see, down here in this graph here, this is 4 to the x, and I found out the constant ratio between y2 and y1 is 1.3863. And down here, this table is looking at 5 to the x, and we get this for our constant ratio. So I filled in the table, and let's move over to another page so it looks fresh. So here's this table, and now what I want us to see is we've got what we have is our derivative over our function equals, well, in every single case, it's equaling some constant factor, some constant stretch factor. So let's say that equals k. And so then we can say, well, the derivative of my function equals k times px. So it's going to equal some constant times the original function. And now this is only, just to be careful, this is only working for p of x equaling some exponential function, so base raised to the x power. So we could write this in, p prime of x equals 0.69315 times 2 to the x, using this idea that we just said. And p prime of x, if p of x is 3 to the x, is 1.0986 times 3 to the x. And if our function is 4 to the x, It's 1.3863 times 4 to the x. And if it's 5 to the x, 1.6094 times 5 to the x. So then the kicker then is, if I have some function p of x equals d raised to the x power, how can I quickly find this stretch factor? How do I find out what these values are? And here's my hint to you. What I want you to do on your calculator, and I'm not going to tell you this answer um, right now. So I want you to actually go ahead and find these values on your calculator. So take out your calculator and find ln of 2, ln of 3, ln of 4, and ln of 5. Find these values. Well, I'm pausing this video right now. So I want you to press pause on the video, find these values, and then press unpause. All right, so up here I have the ln values that I just asked you to find. ln2 is kind of cut off, but here is the ln2 value. Here's ln3, ln4, ln5. Those should look kind of familiar. So now this is not a formal proof, but what we should now be able to conjecture is the relationship between an exponential and its derivative. So by conjecture, what I mean to say is if I have some function, if my function equals b to the x, what is my derivative? Well, going back a page, remember this value here, what is that really? Well, that is ln2. And this is ln3. So what we have, this is ln2 times 2 to the x. This is ln3 times 3 to the x. This is ln4 times 4 to the x. What we just showed, or what we showed through via conjecture, is that if we have some function b to the x, the derivative is, pause it and write what the derivative is. I want you to pause the video and try to make a statement. Okay, you would be right if you said that it is ln b, and that's a number, times b to the x. And what we have is it's just a stretch relationship. Here, here's, for example, if we have the function 3 to the x, the derivative would be ln3 times 3 to the x, and we're graphing that right here. We got 3 to the x and the derivative of 3 to the x, and the relationship is just a vertical stretch. It's a vertical stretch by a factor of ln3. So just to check in to see if see if you got sort of the basics. What would be the derivative of 10 to the x? And what would be the derivative of 7 to the x? And then just a challenge one, what would be the derivative of 5 times 8 to the x? Pause the video and get an answer to these. Okay, well, the first one, straightforward. Just it's 10 to the x, so the derivative is ln 10 times 10 to the x. Second one, also straightforward. ln 7 times 7 to the x. The last one's a little bit trickier, but what we can do is just use our derivative rules. We've got, this constant 5 in front. So this is the same thing as 5 times the derivative of 8 to the x, which is 5 times ln 8 times 8 to the x. Boom. Got it. Okay, so that's the derivative of e to the x. Or sorry, the derivative of e to the x and derivative of b to the x. So just so that we can finish with our understanding, the derivative of b to the x equals ln b times b to the x. Not a proof, just a relationship that we saw.